Okay, so for this problem, we have d1 equals d2 equals 0.1 c, and d3 equals 0.06 c. Assuming thin airfoil theory, what's the lift coefficient CL and the moment coefficient respect to the aerodynamic center at alpha angle of attack equals to 2 degrees. Okay, so the answer to this is actually pretty similar as before. So the first thing we need to figure out is we will need to figure out the all the things. First one, I want to figure out the slope for the airfoil shape. So this is the shape of the airfoil. So as you can see, the slope should be a piecewise constant between each domains, right? So the first thing we're gonna do is I want you to draw a plot for this one, for this one here. Great. So let's just compute the slope of the camber line. So the first one, that would be actually when I compute this camber line, let me see, I would need to compute it sort of within, I would compute the slope. I would say first I would compute in the physical space. So for the first one, it will be d1 over c over 4. That's going to be 4d over c. That's the slope for this one. And for the second block, that would be actually, because d1 equals to d2, so there will be the slope will be 0. For the third part, that would be actually d3 minus d2 over c over 4, which is going to be 4 times d3 over d2 minus d2 over c. Okay, so the last part is actually a minus d3 divided by c over 4. That would be minus 4d3 over c. Okay, so so this is the slope. So remember that in our previous problem, if you look at the previous problem here, we actually did some sort of, so here for that previous problem, we're so lucky that we don't have to perform integration to figure out the capital A naught to capital AN. But here we are not so lucky anymore. So we have to sort of compute some kind of integrations to get the A naught to AN. So in order to get that, what we're gonna do is first, what we're gonna do is we would kind of first mapping the 0 to c into 0 to pi. So for example, in this case here, the x is actually, let me see, the x is c over 2, 1 minus cosine theta. Okay, so for x equals to c over 4 here, the corresponding theta would be, pi over 3. Okay, for the point where x equals to c over 2, the corresponding theta will be pi over 2. For the point where x equals to 3 over 4, the theta actually going to be, let me see, 2 pi over 3. And the last one is, of course, is pi. So now we can try to integrate these things, because if you recall our expressions, A naught, for example, is alpha minus 1 over pi. Integration from 0 to pi, the slope, okay, and the slope will kind of be integrated as as a function of theta, and then times d theta. But here we know when theta changes, the slope actually is a piecewise constant function, right? The slope, right? So so this is why I kind of write everything that I write down this table in order to easier to compute all those integrations here. So for example, for this A naught, what we're gonna have is when we're integrating, so first term is alpha, the second term will be 1 over pi. If we integrate this, we'll first integrating from 0 to 0 to pi over 3. Okay. And the slope is 40 over c, and integrating over d theta. Okay. And the second term would be, because the second block is 0, so I'm going to go from pi over 2 to 2 pi over 3. And the slope is 4d3 minus d2 divided by d theta. Okay. The final term would be actually 2 pi over 3, integrated from 2 pi over 3 to pi, and with the slope of this one, minus 3 over d theta. Okay, so if we integrate these things out, let's see what we get here. We actually get alpha minus 2 over 3c d1 minus d3. So this is the thing we get for A naught. So how about for the A1? For A1, we have, following the formula, we have 2 over pi, integrating from 0 to pi, and the slope as a function of theta, and cosine theta, d theta. Okay, still as before, we're actually gonna just, because the slope only happens in the first segment, third segment, and fourth segment. Okay, so if all you need to do is just do the very similar thing before, and you can actually get I'm gonna skip the answer here, and the answer would be 2 over pi times 4 over c times the let me just write down the final expression. The final expression is basically 8 over 2 over pi c, and square root of 3 minus 1 times d1 plus 2 minus square root of 3 times d2 plus square root of 3 minus 1 times d3. Great. Okay, so the A2 would be 2 over pi, integrating from 0 to pi. Still, we're going to compute the slope, the function of theta, times cosine 2 theta, d theta. And that would give, the answer is 4 times square root of 3 times divided by pi c, and d1 minus d3. Okay, this is all we need actually for computing the moment. Remember that if we want to compute the lift, we only need the first two capital A's. We need A naught and A1. But for computing the cambered sort of the moment coefficient, we need A1. We actually need A1. We need A1, A2, we need A0, A1, A2. But if we compute the moment with respect to the aerodynamic center, we just need A1, A2. Okay, so the answer for the A1, A2, A3, the numerical values are basically, as you can see, are basically here. I just plug everything inside. This is the numerical value I get, A1, A2, A3. And I just need these values. Plug in this formula right here, CL equals 2 pi A0 plus 1 over 2 A1. And C, in terms of the aerodynamic center moment, there'll be pi over 4 times A2 minus A1, capital A1. Okay, so now we're gonna get is we will get the we get the CL as 1.203, and the moment respect to the aerodynamic center at quarter length will be minus 0.21A56. Okay, great. So these are the two examples for the thing airfoil theory. As you can see, they are pretty straightforward. You just all you need to do is just have a clear mind about how to perform the integration. Figure out the first step you need to do is you need to figure out the slope for the camber line, okay? And then the second step is that you need to kind of convert everything from x space to theta space. Usually in theta space, everything is easier to integrate. And then the third step is you need to figure out the A0, A1, and A2, things like that. And the first step is you just plug in those formula to get the airfoil, aerodynamic property.